Hello everyone, Charles here again. In this video, I'm going to provide some commentary about kind of how the simulation infrastructure that we're using in CSCE 611 this semester works. This is an optional video. There's nothing in here that you will need in order to complete your projects for this class. So you should really just watch this if you're interested or curious or whatever. But yeah, so this is also going to be a little bit more advanced content, and I'm going to assume that you're already familiar with Linux and stuff like that, and using the shell and the terminal and things of that sort in this video. So it'll be a little less tutorial-y. But you may want to watch this if, for example, you wanted to explore some more advanced methodologies for testing your code, or if kind of you wanted to do something exciting above and beyond the material for the projects or something like that, or you just kind of want to dig around in the how stuff works, like whatever. And this kind of also serves to document how these systems work for other people that might want to TA this class in the future. So once again, just to reiterate, this is optional content. You don't need to watch this unless you just want to. But hopefully if you do watch it, you'll find it interesting and useful. So let's jump right in. So where I'm at here is this is kind of the reference implementation of our full RISC-V CPU. This is kind of what you'll have. Actually, I think this even has a couple pieces that you won't even get to this semester. I'm not going to show you any of the code, of course, because I don't want people copying code out of the video and turning it in as the solution to the project. So we're not going to do that, but that's okay because we're just talking about the kind of general simulation infrastructure and kind of how all the pieces fit together and things of that sort. Cool. So, and also just FYI as well, a lot of the stuff I'm going to talk about here is also mirrored in the handout that kind of talks about the simulator. So maybe look there first if you have like a specific question, and then, yeah. Okay, anyway, moving on. So there's kind of a couple pieces here. Kind of have this make file that ties everything together. And then the kind of the main folders are RTL, which is where all of the code that you're writing for the class lives. As I discussed in the tutorial video, there's a simtop.sv file in there that has that kind of is the top level, but then kind of other than that, you can put whatever you want in there. And then we're using a program called Verilator, which converts the system Verilog code that you're writing into C++. And so if we go into this build folder, you'll see in Verilator obj, pp, it generates all these C++ files. So if I look at, say, vim vsimtop.cpp, there's all this stuff that simulates, the code that I've written. And kind of, the C++ code's not really human readable, so I wouldn't worry too much about trying to make sense of that. But something we will kind of look at later on in the semester, and it's just kind of generally useful, is that since we are kind of interacting with the simulation in various ways, it can be useful to see where the data is being stored. So it creates all of these different variables that correspond to different signals in your CPU. So for example, simtop.cpu0.aluloex is a specific signal in my design. And if you look at the type defs and stuff, idata winds up just being like a type of int. And so you can actually interact with these values from other code, and that's exactly what the GUI does, is it kind of just directly interfaces with these values, and the C++ side in between simulation ticks and pulls things out and pokes things in, and that's all very well and good. And you can kind of see it's got kind of a logical mapping of the dots are replaced with double underscore dot, double underscore, because of course you can have a dot in a C++ variable name. And kind of this notation of like, top level module dot some other module dot some other module dot signal name, that's kind of a pretty standard notation that's used in lots of Verilog tooling. You'll see that like in GTK Wave, and you'll see that in ModelSim and Quartus and lots of places. So that's pretty standard stuff. And then kind of you'll also notice as well, it's got all these .o files and this .a file and stuff like that, and that's kind of the compiled version of this code. So I'll go back up here. So aside from that, sample programs we're not going to look at so much because that's just risk assembler programming. You won't have that in your projects, or you might if you make it, but we're giving you a folder called that. Scripts has some useful scripts. There's some different code generation going on. So findmem.sh will allow you to search your Verilog code for a memory matching a specific name. You'll use this script later when you set up the simulator to be able to find where your program ROM is stored and where your register files are stored. And then this is also invoked a lot automatically by the makefile and such. Generate config takes certain configuration parameters and generates a C header file out of them. Generate config svh does the same thing but generates a system Verilog header file. Generate memories creates a header file that has certain pound defines that say where to get access to the memories that findmem.sh find. Generate probes.sh is for handling the probes feature, which I'll discuss later. And pack.sh is probably going away because I think that was for previous semesters. I don't think we need that anymore. Or if you have one, it will be different than this one, so I'm not talking about it. So just for an example, I'll do like findmem scripts findmem.sh, and it'll say memory name, and so I'll say something like reg file, and so it'll say there's several candidates, so there's only 3 of them that are exactly the same, so that's interesting. Let's say mem. So yeah, so there's simtop.cpu0.mem and simtop.cpu0.datamem and simtop.cpu0.regfile0.mem. And so if I was trying to find out what my register file memory was, then this would be the one that I would want. And so if I look in build generated memories.h, we can see this is what gets generated by that generate memories.sh script. We can see that it is in fact pound define register memory and then that big ugly string. And so then the various C header files will include this, and then that's kind of how we can handle the fact that different students will have structured their projects differently, and so one person, it might be called simtop.mycpu.myregfile.regfile memory, and that's fine. There's no reason. That's a completely legitimate thing to name it, and we want to be able to accommodate that. So this is kind of how that works. If we look at some of the other stuff in generated, there's config.svh. This is just some widths of things because system Verilog lets to know how wide your variables are. So yeah, not super reset vector. Shouldn't need to change that or really cover it, but that's kind of where the processor starts executing when it's first started up. On sometimes in real processors it won't start at 0. It'll start somewhere else because if you've got a bunch of different stuff in your memory map, 0 might be something other than your data memory. Cool. Let's see what else do we have in here. We've also got config.h, much the same kind of stuff. It does generate this fully qualified path to your Vcd Trace File. That was a deliberate decision. I think that makes things a little nicer because then you don't have to worry about where you run the simulation from. But it also makes the binary kind of, you can't move it to a different system. So trade-offs. The other stuff's pretty much the same as the other header file. In here we have, let's see, probes.h. This is really horribly ugly and disgusting, but essentially this creates a big C macro that creates an ASPrintf command that basically generates, it basically creates a giant printf that prints out all of the values of your defined probes. If you haven't read the handout about the simulation, a probe basically lets you pick a certain signal in your design that you want to have show up in the simulation GUI. And of course you can get all that information by looking at the simulation trace. That's kind of something you do after the fact, not while it's running. So this can be really nice, and I also have a disassembler integrated in here as well, which I'll demo later. All right, so I think that's all the stuff that's generated. So now kind of another important area is support. So I'll go in there. So this is kind of all the stuff that makes the simulation work. This is kind of the back end. A lot of this is code that I wrote. A little bit of it is code that other people wrote. Rars.jar, there's your MIPS assembler that we're going to be using in this class and whatnot. This is actually a patched version because we're doing some stuff with the control and status registers that's a little bit non-standard, so I just patched it up and made a new jar file, and so that's why you want to use this one and not download one off the internet. So there's kind of two front ends to the simulation, CLI.cpp, which is non-interactive, and GUI.go, which is that's what you get when you run make GUI. And so that's actually written in Golang using the Fine User Interface Toolkit. It's written in Golang, so we can use the Fine User Interface Toolkit. If you've written GUIs before, writing a GUI in C or C++ is not fun, generally. If you can avoid it, it's best to do so. So we're actually using CGO to interface with the simulation. So you'll see I've got stuff like here I say like set hex, and then so s.setHex is setting it in the GUI. I have a big state object that stores all that, and then I have like c.readio simstate c.io hex 0. And so this c.readio is actually a C call where you're calling C from your Go code. Cool, a little arcane, but it works well. So, and of course the CLI doesn't need that because it's not a GUI. It's actually very simple type of file. So, got that. We've also got these disassemblers. This is someone else's code, but this lets you take a value, and it's like an integer, and you put it in, and you get a string that is the disassembled risk instruction back out. So this is really helpful for debugging because you can like take your current instruction and you can feed it into there as a probe, and then you can see exactly what instruction is running at that instant in time. And then support.cpp and support.h are also my code, and so these interface between Verilator and Go, because Golang's FFI into C does not understand how to do C++ calling conventions. It doesn't know about C++ objects or classes or operator overloading or function overloading or any of that kind of stuff. So this is essentially a shim that if you look in support.h, you'll see I've got this extern C. So it says if defs __ C++ extern C. So that says if you're compiling this with a C++ compiler, you need to also generate, you need to make these method signatures, you need to export them in a way that a C program can call them. And so you'll see this if you've got somebody that's written a C++ library and they want to call it from C, you'll see this kind of thing. If you work with FFI in other languages, this comes up a lot. And kind of the rest of this just defines some stuff that kind of makes the simulation go. So we've kind of got this concept of a I/O. So these are kind of all of the things on the physical board that you would have been interacting with, or in this case, the GUI, and it's just in an enum, just so we can keep them apart. I've got a concept of directionality that just kind of keeps just to protect in case there's a bug in the GUI, it'll just crash the simulation instead of writing garbage all over it, because that's usually not good. We've got a simulation state object that kind of is just a bucket that stores kind of what's going on at a given instant in time. Some pound defines that map stuff to and from different things. Like I've got this concept of an I/O mask, so for example, there are 18 red LEDs, so if you take 0x000-3FFFF, you'll see that that's 18 ones in a 32-bit integer, and so I use this elsewhere in the in this shim layer to make it so if you try to write something that's 19 bits to the LEDs, it'll just throw away the top bits. It'll just kind of force them to be 0. So it kind of enforces the accuracy, right? Because of course on the real hardware, if there's 18 LEDs, there's 18 LEDs, right? You can write all the bits you want, but it's only going to show 18. Cool. I don't think any of this other stuff's super exciting. Print disassem, utility that prints the disassembly of an instruction. These are just some asserts. So like I can check that when the GUI is calling for reading an I/O or something, if it gives it a bad value, then it'll throw up and then crash the program. But hopefully do so in an informative way and not like write a bunch of junk into memory somewhere and then now it's not technically crashed, but it's not working and now you've got to debug it. It's much harder. And so if you look at support.cpp, It kind of like, so delay cycles is kind of where the simulation advances. So when you click tick 1 in the GUI, this is kind of and there's a couple layers of indirection, but this is the main kind of meat and potatoes of what gets run. And essentially it says stop eval is the top here is referring to the verilator simulation. And so eval says, like, evaluate everything, and then we set the clock to 1, eval again, set the clock to 0, eval again. And then we keep track of the number of cycles. So we also got this concept of a Bcd dump, right? So kind of we're saying, like, we're going to kind of dump the state of all of the signals in the simulation out to a file. Vcd is a value change dump. So it kind of records, like, okay, at this time, this signal went from 1 to 0, or, that kind of thing. And so we kind of assume, like, this is kind of fudging a number of nanoseconds in the VCD, which is kind of meaningless, and it kind of always is when you're running in a simulator, but that kind of makes it look realistic. So it looks nicer when you're looking at it in GTK Wave. Cool. These delay functions, this simulation infrastructure was originally written for CSCE 317. So if you took that class, you might recognize some of this. These aren't pertinent to 611, but in that class we were dealing with stuff like writing a bit-bang do-work controller, for example, and so you kind of wanted to have, I want a delay for 1 millisecond and not for a number of cycles. So we actually had a clock rate that the simulator cared about. With 611 we don't have any of that, so it's not relevant. Reset resets all the registers in the register file for your CPU, and does some delays, and it also presses key 3, which is canonically the reset button for our processor. So if you use something other than key 3 as your reset button, then this will not work. So you should do that. And this is also why you'll notice that the cycle count starts out not at 0, but at, like, I think 10 or 12 or something. And it's because of how it's got these delay cycles in here. So I think when it boots up, I think it delays a little bit and then resets and then delays a little bit more, and then that's kind of gets us to like 10 or 12 or something. Read I/O, like these read and write I/Os are pretty much just big if statements that just look at this enum, and then this is why your top level module can't change, right? Because it's saying res equals s top hex 7. This hex 7 came from the Verilog code. So if you change that to be something like 7 segment number 7, it's you're going to get a compiler error. And you could do something like what I did with findmem.sh. I could have a findsignal.sh that did the same thing, but then you'd have to do it for like all these different IOs, and it'd be I don't want to screw with that. It's easier just to have one top level module that's consistent. It also makes it easier to grade too, because we can plug it all into the same test bench. Write IO, same deal, opposite direction. Look up the IO you want, write the value into it. Ditto, right? And so like this is where the IO masking is happening. So like here it'll say like take the value that we were told to write, mask it with that mask earlier. So if you're writing to say LEDG, which is 9 bits, and you give it 20 bits, then it's just going to throw away the top 11. And of course I say 20 bits, right? But this is really, it's all in a uint32T, so it's kind of really all 32 bits on the C side. So that's kind of where that comes into play. Initialize simulation does what it says on the tin. Turn on some tracing, set trace levels, open this Vcd trace file, comes from that generate config.h. And then these read and write ROM and reg and stuff like that are how like this kind of program memory is what that findmem.sh deal is finding for you. And so this is kind of how the simulator is loading the program ROM into your CPU. And read and write reg, let's see that, well, okay, we don't actually use write reg, but read reg is how the or register monitor on the right-hand side of the simulation GUI works. And then read probes just calls that big macro that's generated by the generate probe script. Cool, so that's pretty much the simulation backend in a nutshell. Go back in there. There's also a test suite, which I'm not 100% sure how much of that we're going to give out and how much of that we're going to keep to ourselves, but essentially what it does is assembles a bunch of RISC-V programs, makes some assertions about what the state of the CPU will be after they're done, and you kind of do a bunch of those, and that's kind of how one way that you can know that your CPU works right. So let's look at this probes.list, and we'll start talking about probes a little bit. So it's kind of got a format here. So you've got int, which means a decimal integer, hex, which is a hexadecimal integer, and instruction, which means disassemble this as an instruction. These signal names came out of vsimtop.h, which we were looking at earlier. And then if we look at scripts, generate probes, you can see that we read that and go through it, and this is super ugly. But so like here, for example, we can say if the format's an instruction, then we need to allocate buffers for it to sprintf the disassembly into. These are stack allocated by design so that this is memory safe and doesn't leak. That's what the asprintf is for in the macro that gets generated. So we do an asprintf into this dest string, which is this is the only malloc we do, and the caller gets this, and the caller in this case is Go that's FFIing into it, and then it FFIs into C again to free it. So because asprintf, if you're not familiar, it's like printf, but it also prints into, you give it a char ***, and it calls malloc on the size of memory that it needs, which is one way that you can handle if you've got a string that you don't know how long it's going to be before you printf it. So that's pretty handy. So then we generate a bunch of format strings kind of one at a time. So hexes, we generate %20s for the signal name, and then ox %x, which generates formats it as hex, and we do %%, right, because we're printfing it in shell, which will consume one of the percents and output 1% literal, which then gets compiled by C into the format string. So we also are having, double the skets, while also we have \\\n, because we want the C compiler to get just \n. So CodeGen is fun. So down here, kind of the other interesting bit is kind of we just take, we slice off the simtop, because that's kind of implied, and we also replace all of the __ dots with actual dots, just to make things a little nicer. And this actually kind of all spits out basically one line of C that is one big, huge printf that does all of that. And so what that looks like in practice, I will boot up the GUI here. So there you see all the CodeGen ticking by. Here we're verilating everything and compiling everything, and then here we go. So this is running a test program that you put in a value on the switches, and it calculates that number in the Fibonacci sequence. So if I tick it ahead, and tick, 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 we can see it's, I guess the fourth number in the Fibonacci sequence is 3. That sounds right. And so PCF and PCEX they're not actually negative numbers, but these are formatted as, you should have done these as hexes, because they're signed decimal integers, so they just happen to have a 1 in the top bit right now. So ditto. Oh, that looks like a little bit of a formatting bug, right? Because it's got 08x0. That's kind of funny. Hopefully that'll be fixed before you guys interact with this. But here we can see the instruction disassembly. So we see right now we're running a no op. So if I do tick 1, you'll see now we're running in the instruction oxffdff06f, which is decoded to jump -4, because it's kind of, I have a busy loop at the end of this program that just kind of hangs forever. So now I'll just reset the simulation real quick so that we can kind of see some more interesting instructions. So here is where it's reading the switches, setting some stuff up, and then kind of here now we're in the main loop for the program. And so you can kind of see all the instructions tick by. You can see the register values updating and stuff like that. So, and these kind of probes can be really nice when you're trying to debug your CPU, since then you can see kind of what's happening in real time as you're stepping through the program, kind of single step style. And you might also want to maybe open RARs and single step it at the same time, and you can kind of cross-reference what's going in what register and stuff like that. So that can be pretty handy. So let's see, so we talked about all of those. What else did we not talk about yet? Looked at the so the final thing I want to talk about is the config.sh file. So this is a big, ugly, technically shell program, because it gets sourced by shells in various places. And this is kind of the single point of truth for all constant values that are relevant to this project, or to kind of this whole simulator, everything, across all of the languages. That's why we do all the code gen and stuff, because I hate having like, oh, well, we're going to have some pound defines in C, but then we have to pound define the same value in system Verilog, and if they don't match up, then they cause problems, and so we kind of just avoid that by just doing it all in one big fat file. So these are the three you'll have to change: program memory, data memory, register. Actually, they'll only have to change two, because I forgot we're not doing data memories. So you'll just change program memory and register memory, and so that was kind of where the find mem.sh stuff came in. Hopefully that was, if you're following this video, hopefully it was apparent, and if you're not following the video, then we will have a hopefully more focused video when it's time to actually deal with that, and we'll talk just about how to set that up, and it'll be more tutorial style. Values you probably don't need to change. Probably don't change these. This is the Verilator binary you want. This is where it's installed. This is header files you need to include when you're compiling C++ code. Project root. This does some nasty stuff that lets you find bash source 0 will let you find the path to the file that's running even if it's been sourced by another file. So that's a little tricky, but that works nicely. All the directory stuff gets built in and from and things like that. Top level module, if you wanted to use something other than SymTop, well, actually, no, you couldn't just change it here, right? Because there's other places that assume it's called SymTop. So, place where stuff gets generated, C flags. We're using C++ 11 standard. You could use it. I guess you could change it if you wanted to. Don't change it for this class because I won't change it when I'm grading it. But just in general, name of the file that Verilator generates, probes list, trace file. If you wanted to not call your program ROM, program.rom, you could change it somewhere else here. These don't change because there's some stuff in the code that assumes that you're using these exact sizes for your number of words of program memory, and data memory is not applicable. And the reset vector is, like I say, 0 because we don't have, we're doing a Harvard architecture, and so kind of there's only one thing mapped into the data memory, and it's the program ROM. And so the way that gets interacted with, right, is you'll see like in the make file, for example, we actually convert all these to, or a lot of them, to make variables by saying source.config.sh and then echo the variables, right? So if I run, if I should do echo project root, not defined. If I source config.sh, now all of a sudden it's media SF source CSCE 611 RISC-V reference. So that's pretty handy. Then in our make file, it's a little bit of a complicated make file as far as make files go. We try to keep everything in the build directory just to kind of keep things clean and make it easier to run make clean, because then you just got an rmrf1 folder. List of all the object files that need to get generated, list of all the archive files that need to get generated. Golang doesn't like linking against object files, it likes to link against archive files. Not sure what's up with that, but makes Cgo happy, so do that. List of binaries to be generated, creates the hierarchy of all the build folders here. Trace will say kind of run the simulation to get the trace file, and then well, actually that's it, and then waves will do that and then also run GTK wave on it. GUI runs the GUI and also calls -- load ROM, because if you just run, because you can just run the GUI on its own, but if you don't give it -- load ROM, it'll just kind of, it'll have nothing load and it'll just sit there and probably do nothing. Halt program. So this is a check that makes sure that the program ROM exists, because of course if you try to run stuff and you don't have a program ROM, then what's it supposed to do? Vcd Trace File, right, so this runs the CLI and it runs it for sim cycles, which is 8192, I think. That's in config.sh. Kind of most of this other stuff is generating object files and archive files, and if you know make, it's not super exciting make stuff. There's just a lot of it. And there's some of the code gen, so when we want to generate header files and stuff, we do these nice pattern rules. So yeah, that's pretty much the make file in a nutshell. It's like I said, if you're in the class, you shouldn't need to change it, and actually probably don't change it, since I will be using the reference version for grading, and so will Philip. So yeah, but it can be good to look at. I think that's pretty much everything that's worth recording as far as how the simulator works and how it's put together. Like I say, this has been kind of just a real kind of fast brain dump of I've been working on getting the simulator working for a while, so I'm just kind of dumping out everything from my head about how it works. And so, like I say, probably not super useful if you're a student in the class. At best, hopefully, if you are a student in this class and you're still sticking here 30 minutes in, hopefully it was at least interesting. All right, I think that is it.